Hello, everyone. Today I'll be presenting a small part of my work, which can be summarized as a random forest approach to assess Troglofauna occurrence in the northern part of Western Australia. So the scope of my problem starts in Western Australia, where the Environmental Protection Authority requires that the companies prove that no subterranean fauna will become extinct due to their proposed activities. So this work here, I'll be focusing on Troglofauna, which is subterranean animal air breathing, living within the geological strata above the water table. So they live in vogues, cavities, fissures, and their occurrence overlaps the mining operations. So this causes a small problem in the decision-making to conservation of the biodiversity underground. However, the data set that I'm using in this work here comes from the opportunistic sampling on mining boreholes. So as you can see here, I have the data set in this area of Hamsley Henge. I choose two calibration areas according to the site sample for Troglofauna, remembering that this is boreholes. And this is biased in the Mount Bruce stratigraphy in the area here. So this is basically where the mining operation occurs. One of the filtering that I did for this data set was because for the same borehole, through the different years, I can have the same animal being sampled again and again. So in my data set, the target columns comes with different presence, overlapping presence. So I had to mark 1 if the target was ever found there, and mark 0 if never found Troglofauna in that borehole to avoid this bias from overlapping presence. So alongside that, I did other filtering, like the cutoff of boreholes without Troglofauna sampling, which means that no specialized person went there for sampling for these animals. So I removed these boreholes, remove of rasters with deprecated resolution that I'm going to use as input as variables. Also split the two calibration areas in the same size for comparison. And I did some basic cutoff of not availables, constant variables, near zero variable variance variables, highly correlated variables. And also for the month of collection of the variables, I did this standardizing, random selection of 50 samples for each month without replacement to avoid bias in the month of collection. With the filtered data set, I compared 4 classification algorithms to decide which one I was going to use in my modeling. So I compared them using accuracy and kappa, and random forest outperformed all of the linear discriminant analysis, random forest, generalized linear models, and neural networks. So I ended up choosing random forest to build this classification in this case here. So I have to split the data set to avoid contamination. This is a recommendation from Khan in this book here, Applied Predictive Modeling. So for both areas, I split the data set to 50-50, 50 to train the model, the remaining 50, 60% to find the optimal threshold, and 40% to validate the model. So as we can see here, the two areas had different optimal thresholds. Area 1 has the closest top left with 0.6. Area 2 had yielding a closest top left with the same value of 0.7. My main concern here was the sensitivity, which means where the Troglofauna is. And I was pretty satisfied with the value. So 0.1 for one, 0.7 for the other. Also, we can see that the Matthews correlation coefficient here is very balanced. On top of that, I did the variable importance plot, and we can see that the two different areas have two different variable importance and different preference for habitats that could be further analyzed using the partial dependence plots, so I could illustrate the effect of the variables in the predicted outcome and have some insights for conservation planning and all the further samples for the modeling. For example, the months of collection, May and November, had some impacts on the outcome. Also, I could have some insight on elevation, also knowledge gap around distance to linear structures, also information about distance to linear structure, and several other insights. By the end, I separated the variables in the ranking, the 21st classified, in 5 types. So for area 1, we can see that temporal variables were affecting more the outcome, and for area 2, it was topographic variables affecting the predicted outcome. By the end, I could plot the predicted probability map of Troglofauna presence. However, it's 2D because I could just have access to raster data set and other 2D features. If I could have access to borehole information, maybe it would be a 3D model. However, it's still contributing to the decision-making areas, conservation planning, and all the insights as well with the variable importance affecting and their correlation with the area that was predicted. This study was possible because of the contribution of the Western Australia Biodiversity Science Institute and also from the funding of the center. So thank you so much for the attention. And that's it.